Okay, in this video we're going to look at another example of using multiple substitutions to evaluate multiple integrals. So we've got here an example evaluating the double integral of y squared over this region bounded by all of these curves. I've graphed the curves here using Desmos since the graphs aren't super simple to think about. So the last example we looked at, the function was a little bit complicated, and that's why we used a substitution for the last example. For this one, it's really more about the region. The function that we're integrating, f of xy equals y squared, is pretty easy to integrate with respect to x or y. But the region, if I look at the region that's actually bounded by all of those curves, it's this little region in the first quadrant here. And that region is not x simple and it's not y simple. So the region is what's a little bit complicated on this one and would benefit from doing a substitution. Alright, so I'm going to make my substitutions this time based on the equations for the region. And I noticed that two of my equations are xy equals something, so I'm going to let u equals xy, and that'll take care of both of these. And then my other two equations are xy squared equals something, so I'm going to let v equal xy squared. Alright, so I'm going to write those over here. So if you remember for our theorem, we had several conditions that we needed to check. One is that the function that we are integrating is continuous. So f of xy equals y squared is continuous everywhere, so we're good on that count. And then the next conditions all had to do with the substitutions or the inverse substitutions. So I'm going to need to solve these equations for x and y in terms of u and v. So there's several different ways that you might do that. So I'm going to do that in a way similar to how I handled some systems of equations when we did Lagrange multipliers. I'm going to multiply this first equation through by y on both sides of the equation, so that will make the right sides of both equations the same, which means I can then set the left sides of both equations equal to each other. So that gives me y equals v over u. Alright, now I also need x in terms of u and v. I'm going to substitute y equals v over u into this first equation. Remember that we want it solved for x, so I'm going to multiply both sides by u and divide through by v. Alright, so those are my inverse substitutions. Alright, one of the conditions was about our region G in the UV plane, and so when we did that before, we took all of the equations from our region R and transformed them into equations from the region V. I'm going to use the fact that I already have them typed up here. So these first equations are for my region R, and then when I make my substitutions, I'm going to have equations for my region G. And remember that our original substitutions were based on the equations of those, and so we'll end up with some fairly straightforward equations when I make those substitutions. xy was u, so both of these first ones become u equals a constant, and xy squared is v, so our last two become v equals a constant. So our region G in the UV plane turns out to be very simple. Okay, one of the conditions was that we have a one-to-one transformation from the region R in the xy plane to the region G in the UV plane. And I mentioned that sometimes you can run into trouble when you have things like squaring, where you might have two different points in the original region, and then those would correspond to the same point in your new region. And so we do have some squares here in our transformations, but the thing to notice is that our region R in the xy plane has only positive values for y. And so even though I have this squaring in my equation here, I won't have any points that are partnered up that will give me the same points. I really should check all the other points, and you could do that by examining other points and being sure that they don't transform to the same point in the UV plane, but we are okay on that count for this particular problem. Alright, the next thing that we need to calculate is the Jacobian. So we need to find our partial derivatives of x and y with respect to u and v. So I'm going to need my inverse substitutions for that. When I differentiate x with respect to u, I'll get 2u over v. And when I differentiate x with respect to v, I'll get negative u squared over v squared. When I differentiate y with respect to u, I'll get negative v over u squared. And when I differentiate y with respect to v, I'll get 1 over u. So for the determinant of that matrix, we're going to do this product minus this product. So when I do that multiplication, this is what I get. I do get some nice simplifications here with some of these. All right, so I end up with 1 over v. One of the conditions for that Jacobian is that that should not be equal to 0. 1 over v is not equal to 0 anywhere, and in particular on the region we're interested in. The other condition was that we have continuous first partial derivatives. So you should notice that these first partial derivatives are not all continuous everywhere. They are discontinuous when v equals 0 or u equals 0. But on our region that we're interested in, u or v is never equal to 0. So we do have continuity of those partial derivatives, at least on the region we need them to be continuous on. All right, so now we're ready to go ahead and use that theorem to set up our integral. We will be setting up our limits of integration on our region G in the UV plane, and so we have just a square there, so that's very easy to set up our limits of integration. We'll have u going from 1 to 2 and v going from 1 to 2. Doesn't matter what order I do those in. I need to make sure that I convert my function to be in terms of u's and v's. If we go back up and look at our integral, we see that our function that we were integrating was f of xy equals y squared. So I'm just going to use my inverse substitution to substitute in place of y. I need the absolute value of my Jacobian. So my Jacobian was 1 over v. All right, I'm going to go ahead and simplify my function a little bit. Because v is going from 1 to 2, the absolute value bars don't do anything there, so I can neglect those. And then I have some v's that will cancel. Okay, going ahead and integrating with respect to v. All right, after I've integrated with respect to v, plugged in my limits of integration and simplified, I get 1 over 2u squared times 3. I'm going to go ahead and pull my 3/2 outside of the integration sign. Okay, after finishing my integration here, I get 3/4. All right, the next video is one about extending this idea to triple integrals, so be sure to watch that one as well.